So standard practice when we're cleaning out data is we want to basically see how much in terms of each of our features, basically our column values, how much of each of these is missing, and how is that going to affect how we deal with the missing values in terms of each of these features. Okay, the is null, which is a function we can find in pandas. It's basically returns to us a Boolean value for whether or not each value in that column is or is not missing. So like, for example, you'll see the output given here. When we total all of the missing values in each column is printed out here. Most of our features, luckily, don't have any missing values associated with them. But we'll notice that here we have age, cabin, and embarked do have a few missing values present. If we were to take the mean of each of these groups, we would instead get a proportion of our data entries in each column as compared to the whole that is missing. So you'll notice that for age, about 19%, almost 20% of that feature set is not entered. So like, as we can see here, this would be one of the entries. Obviously, we don't want to look through the entire, 900 entries in this data set. This is just a really easy and quick way to see, okay, how much missing data do we have in each of our features? You'll notice that for these two, cabin is really large. Cabin is about 70% not included. So we're going to end up getting rid of that column entirely because of that. It's going to be hard to impute that anyway, seeing as it is a categorical data value. See, there's no real way to estimate that anyway. It's not important. We'll probably take that right out. That won't be essential for our regression that we'll do later on. If you notice that embarked up here has less than a percentage of the entire set missing, and that we can remedy pretty easily. We'll go ahead and take out the individual passengers, the individual rows that don't have an embarked value associated with them. The embarked is basically just, as a background note, they're encoded as single letters. It's basically just the port that each passenger departed from. And there are a couple different ways to do this. The main two that I will go over. The first method is by querying each of the groups. Essentially what that looks like. And first of all, we drop the cabin value from the column set entirely. And that's simple enough with drop. You've probably done this before. But does anyone know why we have to specify the axis in this method?
I don't know what it even means by axis. Like, what is that?
So in this case, what was that?
It means rows or columns.
Yes.
Oh.
So for axis, the input set, actually, if you were to look at the documentation for this would be very apparent. Oh, well, I don't have it here. But if you were to look through the documentation for this, it actually will note that axis takes in either 0 or 1, 0 being the default, and also specifying the rows. If you put in 1 for axis, it'll look through the column labels essentially for cabin and then remove it. If we don't include this, it actually returns a key error, which just means that Python wasn't able to find cabin in the rows, which makes sense because all of our indices are numbers. So moving from that, we can pretty much solve our issue with the embarked data being missing by querying out the embarked column. And essentially what this is, when you query like from your data frame or something, you'll put in a string that has some sort of comparison value like this. And it basically just returns every entry in the table that has a viable value for embarked. Right, so wherever embarked is embarked, which is essentially wherever there is a value for embarked, it'll return true, and it'll bring a table that has all the complete entries for that. We'll check again using our isNull method. And if we sum the column for embarked specifically, we'll see that there are no more missing values. It successfully got rid of the 2 that happen to be missing. And that's in line with the size of our data set now. You'll notice that it was like 891 before. Now the entire size has gone down by 2, which is great. There's not too much data loss happening vertically. Second way we can do this is using the drop NA method. This is another pretty simple way to do it. And in this case, we will drop and subset on the embarked column, and it will drop any value in that column that it finds that is missing and keep all the other entries. The result is the same. We still have 889 entries. Pretty straightforward. Okay, now that we've dealt with both the cabin and the embarked columns, and those are all cleansed of any missing values, we still have age to deal with. If you recall, age had a lot of missing values, about 20% overall was missing. And that's not necessarily large enough that we can totally discard the column entirely. Age might be a very important factor for a regression, so we're going to want to keep that. But how do we do that? Seeing as there is that much data missing from it. One way to do that shown here is querying by age, removing well, I guess first of all, we'll take a look at what the distribution is in terms of ages that are entered and ages that are not entered. And this is just a kind of a way to visualize the proportion of individuals who survived versus who did not survive in each of our sets. So for the non-present ages, that'll be about 20% of our entries. This is the distribution in terms of those who survived and who didn't. And this is the remaining data set that is present. Same goes for class as well. So it seems from these graphs, we can tell that the distributions are relatively similar, but noticeably there are much fewer age entries for those in certain classes as opposed to the whole. So we might be missing out on some important information here. We want to make sure we don't alter our distribution and create any biased training sets as a result of this. So we're going to want to keep our age values as much as possible. And for this, we're going to fill in using this function fill NA to all values that we find in our data set that are missing. And we do this by imputing the median or the mean, whichever is most useful to you. For each, in this case, we're going to go by class. As shown here, we're going to take the median age for each class, 1, 2, or 3, and impute values for each passenger according to the class listed. Right, and we can do this because everybody in this data set has a class associated with them, so we don't have to reconcile anything like that. And this is just what the function is. Essentially what's going on here is we're going through each of the 3 classes listed in this loop, and we are locating individual passengers that have that certain class value associated with them. And then once we subset the data that way, we fill in any missing values that are scanned according to the age value median for each class. And that's going to be the same for all missing values. Any passenger that has a missing value for their age feature is going to end up with the same age, but it's going to be roughly what the expected value for that that class is anyway. So hopefully this doesn't affect our data too much. And at the very end, we find that we've successfully gotten rid of all of our missing entries. So in this example, it's relatively straightforward, but as long as you understand how to use data frames and how to use pandas, it's, these functions apply to pretty much any tabular data that you might encounter. So that's a pretty simple explanation about that. We're going to go over to the next part, which is linear regression. We're going to talk about this a little bit. I'm sure we've all encountered linear regression to some extent before. How many of us have, like, encountered this in like a class or something? Anybody? Yeah. This is probably the simplest, and that's why we start out with it. This is probably the most straightforward and simple form of modeling in data science. This is usually explained first just for the purposes that it's the most straightforward, usually pretty easy to understand. But this is a form of supervised machine learning. There will be other supervised machine learning types that build off this concept, but ordinary least squares, which is also another alias for linear regression, is just the method by which we estimate what the parameters are in a model, right? And we'll see what that looks like, what the equation looks like soon. Yeah, just as a recap, and say an example, this would be an example of a data set in which there are different features of like a house, for example. And we have a feature matrix, which has all of the values for each column. So like number of bedrooms, number of bathrooms, these would all be features in our feature space. And our label, which is the price, which is the feature we're looking to predict on, given all of the features in our on the matrix on the left, we want to find what the price is or our label is, right? The fundamental equation looks a little like this. I wouldn't get too hung up on the mathematics behind it or anything. But if you've seen this kind of thing before, it looks very familiar to like basic graphing, where you have an equation for a line and you have an intercept, a slope, and these all have values associated with them. The only difference here is that there is a random error component associated with regression. In a lot of cases, the random error component will follow some sort of distribution. Like, for example, it'll be specified that it's, you can assume that it's normally distributed or something, right? The random error in this case is just the difference between what the values in the data set are and what's the difference between those values and what's expected or what the true value of the population is. And since that's a little vague, we'll take a look at it. Simple linear regression is where we have essentially a relationship between two variables. In this case, for example, the square footage of a house and the price of the house. Pretty reasonable to expect that with a lower square footage, we'll have a lower price, and we can effectively model this behavior by creating a line that minimizes the difference between the points and the line that is the expected or predicted in this case. Sum squared error is basically just a metric by which we minimize the error of this function. So the way we figure out that this line is the most optimal predictor is by minimizing the error, which is the difference between the actual points, the dots, and the line itself. If we have a line that inaccurately fits this information, the sum squared error would be much larger. Reasons why we take the square too, just a couple notes. There would be, for example, if we just took like the difference of these points in the line, there would be no punishment essentially for lines that predict under the line. So like the two or three points that we have below. By squaring, we know that these values are also incorporated into factoring which line is most optimal. This just also happens to have a lot of nice mathematical properties, differentiability. Again, don't worry too much about that. I'm not going to go over any high-level math on that end, but just something to keep in mind. That's why sum squared errors will be used in terms of regression. A lot of the time, while linear regression does appear, at least on the surface level, to be a very simple, slope intercept sort of model, sometimes our data is not so easy to conform to that kind of model, right? Sometimes we're our information will follow some other distribution. Sometimes it will be nonlinear in nature, and there are ways we deal with that as well. A lot of time we can transform the features in our data set to make it a little easier to model this way, right? And that's essentially what feature engineering is, data engineering is. There are some individuals whose entire careers are based off of just modifying data for modeling and not actually doing all the statistical programming behind it. So it's a pretty big area. So aside from simple linear regression, we have polynomial linear regression. And like I said before, regression is not always a straight line. In this case, our equation is a little more complex, but it's akin to something we've seen before. If our data follows a more parabolic curve, we might be able to model it that way. Multiple linear regression is also a more complex version of simple linear regression, and it's expanded so that instead of just taking the square footage of a house and trying to predict the price based off of that alone, we can take a lot more features in addition to that. We can take the number of bedrooms, number of bathrooms, like the matrix we saw in the beginning. We can take all of these predictors and give them different coefficients, different weights that all factor into what the final label is, the final price, which is Y. Again, the random error component is always here. It is always present because in reality, no data set is perfect. Every data set will have some element of uncertainty to it, some element of noise. This is important to remember for later because we will use the random noise, the error, to figure out if our data set is well equipped to be modeled by linear regression. We'll see what that means in a minute. But yeah, in the case of multiple linear regression, we're actually regressing on more of a plane, which is, you know, greater than a one-dimensional space. For the Titanic data set, we don't really do any of this. That's not exactly, so I wouldn't worry about that too much. But metrics to see if we have a good model. I think for the notebook for this week that we will go over next week, we'll be using R squared and adjusted R squared as a primary metric. If you've used Excel at all, if you've done any like experiments or anything like that for any of your classes, a lot of the time you will have to, you know, create an adjusted R squared value. R squared value, generally, the larger the value, the better the line fits to your information. Mean squared error is another one. So similar to our sum of squared error, this is just the average of all our, essentially the average or the mean taken across all of our values. Again, we're trying to minimize as much as possible the difference between each of our data points in the line itself. And this equation, you know, penalizes differences in values that are much greater than others. So if we have a point that's really close to the line, it will factor into this a lot less than any points that are very far away. I said before that the errors, the noise, looking at how that is important to deciding whether or not we have a good model or not. And that's definitely the case in terms of the distribution of residuals. We're going to take a look at how to make these kinds of plots next week. But essentially, you can think of the residuals as sort of the error in the data. So all these points represent essentially your data and how it's distributed across your model line. You'll notice that there are 3 plots listed up here. The first one represents something that we would like to see when we create these plots. You'll notice that throughout, from left to right, you can tell that the points themselves are individually relatively random. They happen to be approximately the same distance from the line throughout. It's very homoscedastic. That is what that means. It means the variance is constant throughout. An example where this is undesirable is in the case of heteroscedasticity. And that's essentially where our error terms increase or decrease in variance. So for example, in this case, you'll notice that our points start out very close to the line, but then fan out over time. That shows essentially an increase in variance. This indicates to us that maybe a simple linear regression model is not optimal for this because there is a lot more variation in the information later on as opposed to in the beginning. In this third example, this is likely data that is completely nonlinear in nature. This indicates to us that perhaps the model we have is not complex enough to fit our data. Perhaps we need to create something in a higher feature space. Perhaps we need more something that's more polynomial in nature. So you see that like there's a sort of curve that happens almost parabolic. And that's essentially what that means. These are just a few other metrics that we use. I include this slide just because it's good to have a familiarity for these terms, but honestly not super useful for starting at a data science project. The ones you probably have seen before are the F-test and the T-test. You've taken like a very basic stats class. You've probably done some sort of F or T-test. And these are just different ways to evaluate different experimental types. Depends on the situation too, so. I don't have too much for you guys this week just because the terms are happening and everyone's busy. I know I am very busy as well. But the one thing I do want you to do, or at least try to do before next week, is revisit the data set you picked out in week 2. I hope you remember I asked you in our second week to take a look through some sort of data science database of some sort, find a data set that interests you. All this information's in our past slides too, if you need a refresher, but take a basic data set that you've found in the past and try to see, using the methods that I went over today, if you can find any missing values. And if there are missing values, see if you can handle them in a way that preserves much of the data set as possible. Like with our Titanic data set, you'll know that we were able to preserve almost all of the entries except for 2. And that's kind of the thing we want to go for. And I encourage you to practice this as well, just because it really is a first step if you are looking to get involved in a project in the near future. Other thing I will add to this, make sure to stay rested, stay safe, stay healthy. And yeah, don't study too hard. And I will see you guys next week.
Thank you.
Mm-hmm. Again, I will be here for a few minutes after, just if you have any questions about anything. But yeah, see you guys next week.